Welcome back. In this lesson we're going to look at rational functions. And you can see that a definitional for a rational function right here. That's a ratio of polynomial functions. So a polynomial is a variable or a grouping of variables and numbers. So an example of a rational function would be one polynomial over another polynomial, or x over x plus 2. We could have something a lot more complicated if we want to. We could say x squared plus 2x minus 4 over, say, x to the 5th minus 3. Really complicated stuff. But basically we have a variable on top and a variable on the bottom is what we're looking at. So we're going to learn a lot of different vocabulary in this lesson. So pay attention closely to that. So the first vocabulary term we're going to look at is a continuous graph versus a discontinuous graph. And I have examples of both. So I encourage you guys to put these both in your calculator and see how they differ. Before we do that though, from the last lesson, we looked at vertical asymptotes. So vertical asymptotes happen when we have our denominator equal to 0. So is there any value I could put into x there to get it to equal to 0? We have a 1 here, a plus 1, so that means we need a negative 1 out of here. And we're never going to get a negative 1 out of here because this value is squared, so it's always going to be positive. So there's not going to be any vertical asymptotes here, which is kind of why it's going to be a continuous graph. So let's look at my calculator here, and let's look at the graph of x up here, and on bottom we have x squared plus 1. Let's take a look at that. And if I zoom in a little bit, it's just going straight across, and it is continuous the whole way. There's no gaps in it. So let's take a look at my other graph, y equals x squared plus 4 over x minus 1. It's a little bit more complicated. Alright, I'm going to put a fraction in here. Let's look at x squared plus 4. Uh-oh, that didn't go out right. X squared plus 4 divided by x minus 1. X minus 1 is equal to let's take a look at this graph. I'm going to zoom out a little bit. Try to anyway. There we go. Alright, so this is a different looking graph. Never seen anything like this before in class. So, kind of looks similar to our reciprocal function graphs from earlier. If I do a little math here, I can get this to equal 0 in the denominator, so I should have a vertical asymptote at, if I plug in a 1 here for x, I'll get 1 minus 1, which is 0, so that should be undefined. So at 1 equals x, or x equals 1, it should be undefined. So let's go back and look at my graph here. Let's do a table. And there you go, at 1 it is undefined. The values are everything else except for 1. So that makes it discontinuous. So it is not continuous, the graph. It has a point where the line does not extend all the way on the x-axis. This, on the other hand, is going to be a continuous graph. So we have a point of discontinuity. The point of discontinuity will be at x equals 1. Alright, let's look at a couple more things. So discontinuity, we can have two different kinds. We can have a non-removable and a removable kind of discontinuity. So our non-removable discontinuity is going to be an example like this. So if I plug in -3 into this graph, I'll get an undefined point, right? So that is going to be non-removable. It's permanent. We have a point of discontinuity at x equals -3. Over here, we have the same thing. If I plug in a -3, we're going to get an undefined point, a point of discontinuity. But if I do a little math magic here, and I factor my top, so I'm going to factor this numerator here to x plus 3, x plus 1, hopefully you all remember that factor, over x plus 3, I can see that my x plus 3's cancel out, and I get y equals x plus 1. So if I plug in -3, I actually get -2. So this is what's called a removable point of discontinuity. So I need to actually write a definition out for this in the problem to make it a removable point. So I can say that y is equal to, this fancy parentheses, x squared plus 4x plus 3 all over x plus 3 if x does not equal -3. And I'm going to say that this equation is equal to this -2 if x is equal to -3. So we're going to bypass this point of discontinuity. So with this given definition, now we have a continuous function. All right, that's not too complicated for you guys. We'll ease into it. So we have non-removable and removable points of discontinuity. So I can factor some things, move some things around, and cancel out the denominator. We no longer have our point of discontinuity there in that graph. All right, so let's take a look at one real quick. Check the time, we're okay. All right, so is the following function continuous or discontinuous? If there is a discontinuity, then is it removable or non-removable? So looking at this, we can graph it maybe and see some things. But I have a couple binomials here, so I think I can factor them. Let's do that. So I know x squared minus 9, if I factor that, it is x plus 3 times x minus 3. You guys can make the box and try and figure that out on your own if you can't do it in your head yet. And I know the bottom is going to be, let's see, x plus, no, it's going to be x minus 3 and x minus 2. So by looking at this, I have two values where I can make the denominator equal to 0. So if x equals 3, that would make this 0, and 0 times this would be 0. So that would be a point of discontinuity. And also at x equals 2. So those are my 2 points of discontinuity. And now to see if they are removable or non-removable. So I could cancel this x minus 3 out. So this one would be removable. My 3 is going to be removable. My x minus 2 I can't cancel out. That's going to stay there forever. So it's going to be non-removable. All right. So is the following function continuous or discontinuous? Say this is discontinuous, right? Because we have a non-removable point of discontinuity. Then is it removable or non-removable? Well, we have a removable one right here in x equals 3 and a non-removable point of discontinuity at x equals 2. All right, one last thing for this lesson. This is the easiest part. We're going to take a look real quick at horizontal asymptotes. A couple little laws with horizontal asymptotes. You guys should know by now that a horizontal asymptote is a line that our function is never going to cross. It's going to go horizontally. So if what we're looking at these is we're looking at the degrees of our variables. So this is a degree of 1. This is a degree of 2. If we have a higher degree on the denominator, then my horizontal, put HA, horizontal asymptote is going to be equal to 0, always. If the degree in the denominator is higher than the numerator, so 2 is greater than 1. If I had a 3 down here and a 1 up here, it'd still be the same. My horizontal asymptote is always going to be at 0. If it's the other way around, and my numerator is higher than my denominator, we have no horizontal asymptote. All right, no ha. So no horizontal asymptote. And lastly, if we have the same degree, my horizontal asymptote is going to be whatever value these are, 6 over 2, 3 is 6 over 2, right? Whatever the coefficients values are simplified, is the word I'm looking for. So we will have a horizontal asymptote at x equals 3 for a problem like this. Also, if I had something like y equals 4x to the 5th over x to the 5th, here we're going to have a horizontal asymptote. So you can guess at x equals 4. There's a 1 here, so it'll be 4 over 1. Horizontal asymptote at x equals 4. A lot of information to take in here. I hope that you got it all. Have a great day.